Okay. So last time, and these first few videos are going to be a little, I don't know, a lot of theory, right? So not a whole lot of examples yet. We will get to some examples a little bit, but the first couple of videos are probably going to be a little dry, a lot of theory, and we just got to get through them, and that's okay. So this is where we finished off, talking about sustainability, talking about, again, a reservoir being a body that we can add energy to or withdraw energy from without experiencing significant change in energy, change in temperature. But nothing is infinite, except for maybe the sun, as far as we're concerned. But even that's not infinite. Anyway, let's not go, it's not necessarily our focus here, okay? Sustainability is important. That's something you will learn more about as you go along. Okay, a couple more terms real quick. These are other terms we can apply to a thermal energy reservoir. So a source is any reservoir that supplies heat. A sink is any reservoir that absorbs heat. If we were to, you can go Google images of heat sinks, and you would find a big hunk of aluminum that we would strap to an electronic device that is basically, you use that hunk of aluminum to channel or to diffuse heat away from your sensitive electronic device very rapidly. Excuse me, sorry. Okay, so that's a little bit about reservoirs, thermal reservoirs, sources and sinks. Let's talk about engines. So it's real easy to convert convert work into heat, right? It's real easy to generate heat. That's kind of the basic idea. If I've got some kind of electronic device, right? Let's say I go to a big box store and I go purchase a heater, right? And so I just plug that into a wall. Boy, that's terrible. Wow. There. Okay. So I plug this heater into the wall. That's going to pour electrical work in, and that's going to kick heat out. All right? We can go buy an electrical device that consumes electricity, generates heat by doing so. That's real easy to do. Okay? Now, let's say, and I always like to make this joke and say, all right, well, let's say I'm going to go camping then. Right? And practice our social distancing. So I go camping. I don't know how long I want to spend trying to draw a campfire. That's not terrible. As my drawings go, that's probably not bad. Let's say I go camping and I build me a nice big campfire, generate a lot of heat, right? Let's say I take that same heater, the same electric heater, I forget my phone charger for whatever reason, and let's say that I cut the plug off of that electric heater, and I take the wires and I try to hook it up to my phone charger. Right? Now we've already said it's real easy to take this electricity and turn it into heat. That's easy. Now the question is, can I take this heat from this campfire and use this heater to generate electricity out? You guys hopefully are laughing at me, right? No, that doesn't happen. Absolutely not. Now, I say that. There are actually devices you can go buy that you can set little embers from your fire you can actually put into this little can, and that can will actually do this right here. It'll take heat from the fire source and actually generate electricity. And that's okay. It is possible. But you really have to be intentional to do that. It doesn't happen spontaneously. This will happen spontaneously. Electricity to heat, spontaneous. And that's actually the second law at work for us. Taking this heat and turning it into electricity, that's not anywhere near as easy. Right? That's just not going to happen. However, a heat engine is a device that does just that. Heat engine is a device that will actually consume heat from a power supply or from a heat source and actually convert some of that heat into useful work. Right? So, the basic idea of a heat engine, I'd say a device that's going to receive heat from a high temperature source. You see here, this is a graphic from the Changle and Bowles textbook. Receive a massive amount of heat. You see how wide this is. Lots of heat in, going into the heat engine, receives a lot of heat from a high temperature source, converts part of that heat into work going out. We can use this to generate electricity, turn a textile mill, power a vehicle, whatever we want to use this work for. But we can't turn, and we've tried to turn all of this heat into work. Theoretically, there's a point we can do that, and that's the third law of thermo we can talk about later. What we know is we can't turn all of this heat into work realistically. Some of it is still going to stay heat. Okay? We can convert part of the heat to work. Whatever we can't convert to work, because the energy must be conserved, it's got to go somewhere. We've got to reject the remaining heat to some low temperature source. In an engine, you want it to repeat. You want it to operate in as long as you can provide a fuel source. You want that engine to continue to run. So we've got to operate it in a cycle, so it'll operate as perpetually as we can. Now, another term here, working fluid. That is the substance that we use to move heat from one part of the engine to another. Move the heat throughout the cycle. And we tend to use water. It's not very corrosive. It's not toxic. It's fairly readily available. But the biggest thing about water is it carries a huge amount of heat before it will increase in temperature. So there's many advantages, but that's one of the biggest advantages is the sheer amount of heat that the water can absorb and carry from one point in the engine to another. So that's the working fluid, the fluid we use to move heat around. Now I'm going to draw this with you. So as we've talked about, I think I've mentioned this before, as you're watching these videos, you should be taking notes just like you were sitting in class. I'm going to start on a blank sheet of paper here. Okay. So I would suggest taking notes as you go along. But, I mean, if you can sit here and watch me and listen and get everything you need, go for it. But I think most of you are probably going to want to take some notes as we go along. So I'm going to draw this heat engine with you. This is kind of a fairly standard diagram. Excuse me. I've not been talking much, so I just drank a bunch of coffee, so I'm a little rough right now. I think I'm okay. Anyway, here's the idea of a heat engine. I'm going to draw a basic heat engine diagram with you. You're going to have a heat exchanger up at the top here that we simply call a boiler. All right? Now that boiler is going to receive heat in from some high temperature source operating at a high temperature. Some fire, we can use coal fire, we can use a nuclear reaction, we can use the energy from the sun. As long as it's high temperature heat, it'll work just fine. So the idea is in the boiler we're going to have high temperature, high pressure. We're going to feed the boiler with high pressure water or high pressure working fluid. And it's going to come out of that boiler at a high pressure. There's nothing in the boiler here that's going to increase the pressure. So I'm going to have high temperature and high pressure working fluid coming out. Steam, typically. High pressure, high temperature water vapor. We're going to run that high pressure, high temperature water vapor through some kind of a turbine or turbine. Now as that high pressure, high temperature steam works its way through the turbine, it's going to expand. It's going to come out at a low pressure. It's going to come out, I don't know, we'll say medium temperature. Not cold. We'll get it as cool as we can get because we want to get as much energy out. This is where we get the work out of that turbine. Now from there, so the boiler is just a heat exchanger, and then on the bottom we also have another heat exchanger typically we call the condenser. Okay? So we feed the condenser this output, this low pressure, medium temperature working fluid. Typically it's water. And we're going to expose that fluid to some low temperature sink. Some sink operating at a lower temperature. So the idea is that the working fluid in here can lose heat to the condenser. Remember, I put a real big thick arrow up here. I put a lot of heat in up here. I get a little bit of work out, and I can get a little, but then I've put all this energy in. I can only put some of it out as work. So I've got to reject what's left down here to some low temperature sink. So the idea then is I'm going to come out, it's going to come out low pressure. There's nothing in here that's going to change the pressure. It'll actually drop a little bit realistically. But we're going to, for our purposes, we'll assume it's a constant pressure. And we want it to come out low temperature. Or it's going to come out lower temperature because we're removing heat from it. Now, what we normally do, see, here's the thing. I need high pressure going into the turbine. Right? I need high pressure here at the turbine. Well, there's nothing in the boiler that's going to increase the pressure. We're just adding heat. In fact, we want it to be reasonably constant pressure. So what we've got to do is we've got to increase the pressure somehow. And what we normally do is we put a small pump here. We use that pump to really increase the pressure of the fluid. Now that pump's going to require a little bit of work input. If I can get in the condenser all the way down to a liquid, because liquids don't compress, I don't have to put very much work in to a liquid to get it to come out high pressure. Now ideally that pump should not increase the temperature too much. That means if it does, that means I've got to probably have a problem in my pump. So it's going to come out, it's going to go in low temperature, come out low temperature. The goal of the pump is to increase the pressure between the condenser and the boiler. Get a very high pressure here, so if I put high pressure liquid water in the boiler, allow it to boil off, it'll come out high pressure, high temperature steam, and the process repeats. Okay, so if I were to set up a first law analysis for this heat engine, well, we're going to write a first law equation. The first question we have to ask is, what crosses the boundary? Right? And if we think about that, well, what does cross the boundary? Well, I've got work. I've got heat. Let's say Q out. We'll use L later. I've got work and I've got heat crossing the boundary, right? You see any mass crossing the boundary? No. It's a closed system. I mean, it does kind of depend on where I draw my boundary. If I draw my boundary there, right? It's a closed system. There's no mass crossing the boundary. all the working fluid is trapped going through this cycle. So it's a closed